Welcome to APSC 2008 Digital Electronics and Computer Interfacing. This is Module 2 on electronic components. So what can you expect from this module? So you will be able to understand basic electronic components that we will be using in this course, such as resistors, potentiometers, switches, LEDs, light emitting diodes, LDRs, light dependent resistors, diodes, transistors, and logic gates. And also you will be able to design circuits with these components. And another important thing we will be learning in this course is Tinkercad, which helps you assemble and simulate basic electronic components. So this is a free portal that is offered by Autodesk. So we will be learning that. And we will also learn how you can effectively use breadboards and multimeters for prototyping. So let's get started with the most basic component, that is called the resistor. So resistor has two purposes. One is to resist the flow of current in a circuit, or it can impose a voltage reduction in a circuit. So resist the flow of current in a circuit. So let's say an LED, like we'll be talking about that later in this module. However, LED can carry a maximum current of 20 milliamperes. So we know the current is directly proportional to voltage. So when you have higher voltage, more current is going to flow through the circuit. So if you connect it to a 3 volt ampere, some current is going to flow. We don't know how much though, but we can do that in Tinkercad. However, let's say instead of 3 volts, we are connecting 9 volts. The voltage is higher, so more current is going to flow through your LED. So this might damage the LED. So what we do is we put a resistor in series. So what this resistor is going to do is it's going to limit the current going or flowing through the circuit. So this is called a current limiting resistor. And another scenario here is, let's say you have a component, that can be any component, which needs a 5 volt supply, but what you just have is a 9 volt battery. So what do you do with that? So what you do is, just if you know the dynamic resistance of the component, you can connect a resistor in series with that component, so the rest of the voltage is kind of dropped in the resistor, and the electronic component of interest here is supplied with the current, like say the 5 volt. So from 9 volt we kind of reduce some voltage with the resistor. The 4 volt is kind of dropped across the resistor, and then the remainder of the 5 volts is applied across the electronic component. And this is the most important use of this basic component called the resistor. We also have another form of resistor, which is a variable resistor. So sometimes a fixed resistor can be, like say if you have like a circuit where I wanted to change the current or change the voltage while I'm operating the device. So at that point of time, potentiometers or the variable resistors come into play. So most of the knobs, say you see in the car, that has a gradual variation. There are something also called the rotary switches, so that is different. So you will have different levels, 1, 2, 3, 4, 5, like that. But potentiometers usually are say it's like a sliding contact, you will be able to see. So on the kits you would have received, you have these resistors, and you also have a potentiometer, so which will have a rotary dial on that. So that is the kind of resistors we have. Now let's dig a little deeper into resistors, what happens in a resistor. So before we jump into what happens when a disconnect in series and parallel, we need to understand two rules. It's called the current rule and the voltage rule. So the current rule states the total current arriving at a junction is equal to the total current leaving that junction. So for example, this is a junction. So we don't have any way of storing or keeping the charges here or electrons here in this junction. So anything that comes in have to go out. So if you see, like the current 2.1 amperes is coming to the junction, and the 2.4 amperes is coming in to the junction. And there are two other currents or like wires leaving out, like that carries 1.5 amperes and 3 amperes. I believe like that is 3 amperes, 3.0. So the period is missing there. So that's so altogether you have 4.5 amps coming in and 4.5 amps going out. So there's no charge. So the current coming in equals current going out. So that is the current rule. And we have something called the voltage rule as well. So in the voltage rule, the sum of voltage drop in a series equals to the voltage, the voltage raise or like voltage across the circuit, or you could also say the voltage rise in the circuit. So what it says is, let's take the circuit. So this is a battery, this is a voltage raise. So you have a voltage raise here. So this voltage raise is equal to the voltage drop in this resistor V1 and this resistor V2 and this resistor V3. So VT equals V1 plus V2 plus V3. If this is a 9 volt resistor, let's say 3 volts drops here, 3 volts drops here, 3 volts drops here. So altogether, the sum of this voltage is going to be equal to the drop in these 3 resistors. So that is the voltage rule. So applying those rules in a circuit, so we have this. So what happens when you connect, like say, when you have like more resistors connected in series, what you can do about it? So if 2 or more resistors are joined together end to end so that the current remains the current flows or the current remains same in that circuit, the effective resistance of that series resistors can be added together. So let's say you have 3. So because this is because of the current rule which we read in the previous thing. So the current is same everywhere in a series circuit. Using that, we can find, if we have like, sorry, just give me a second. No. Go back. Yes. So if you have 3 resistors connected in series, and you can add them up with just like you can add them up and then use that for calculations. So that is resistors. So that is the resistance of the resistor connected in series. So what happens if you connect them in parallel? So in this case, if you see, the current is not going to be the same because it is not connected in series, it is connected in parallel. But what will be the same is the voltage. So in a parallel circuit, voltage across the components will be the same. So in this case, if we wanted to add the resistance across the circuit, you are going to use this formula. 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. And you can, even if you have 1,000 resistors connected in parallel, you will be able to use this formula and like just calculate one resistance that is equivalent to all those. So here is a small example. So 1 over 330 plus 1 over 68, you add them together and take the inverse of it because it is 1 equivalent. 1 over the resistance equivalent is equal to these. So when you get this number, make sure you take the inverse of that to get your equivalent resistance. So that is resistor in parallel. So the two most important thing, when you have resistors connected in series, you can just sum them up. If they are connected in parallel, you will have to use this formula to calculate the parallel resistance. Another most important specification of a resistor is the power rating. So we say, yes, the resistors do, what to say, like it does impede the flow of current. It, what to say, it also reduces the voltage. So what technically happens is like it kind of takes some of the energy from the power supply actually. So what happens to this energy? So this energy is often dissipated, or like say everything is dissipated as heat. So heat is kind of the easiest thing. So mostly heat is the output in a electrical component. So for example, even a light source, let's say you have an LED. So the light which is emitted might be, yes, like 20 or 30% of the energy that is used by the component. The remainder is all predominantly emitted as heat. Although like these days the LEDs are like performing much better, so the efficiency is like much better. However, heat is the most common energy that is kind of emitted or like say wasted, as long as it is like a waste. So in a heater that is like useful, but in other components, let's say in an LED, like we are expecting light and not heat. So in that case it is considered a waste, but like that is the common waste like you will find. So if you want it, the most important thing is all the power that is, all the energy that is consumed by the resistor's dissipated heat. So at what rate it dissipates, that is very important actually. So if the resistor is rated for a particular power rating, and if you apply too much voltage or too much current flows through that, the power, and if the power dissipated by that increases over the power rating, like that might like literally explode. So we don't want that. So always we'll have to know like what is the power rating of it. So how do we calculate the power rating? So very simple, the formula that we used for power calculations, V times I, voltage times the current. So here we're dealing with resistance, so I squared times R, or we say V squared times R. So using that formula we can get the power that is actually dissipated. But usually if you get the specification sheet, or like we call it the data sheet, so in that data sheet, if you see, they will specify what is the power rating. So the most most of the resistors that you find in your kit is 0.25 watts. It's not that much. So as the watts increase, so probably if we go to the picture like that we had in the first, maybe in here. So the larger, so these ones are like say very small, so 0.25, 0.5 watt. So slowly it kind of increases. So if you see, the size kind of increases. So when you have a bigger resistor, which means you have like say more surface area, more heat dissipation, so the watts rating, or like the power rating, is going to be like higher. So make sure before you use a resistor, make sure like for a simple circuit like which carries like few milliamperes of current, you don't have to worry about that too much. But when the current increases and when you put a resistor in series, make sure you calculate the power dissipation and then like kind of energize your circuit. So that is resistors and power rating, and I will see you in the next section.